We started today with this mental math starter. You had to draw a four-sided figure in which all the sides had the same length, but it was not a square. And what you guys ended up drawing, if it couldn't be a square and all the sides were the same length, it had to be a rhombus. And so I can't really draw this very well with my pen, but we talked about the proper way to mark when all four sides are equal. And we didn't say it had to have 90, in fact we said it could not have 90-degree angles. The four-sided figure with all the angles as right angles but not a square was a rectangle, and we put the marks in for having a 90-degree angle. You put a little square in each corner. Alright, can't draw that very well with my mouse. A four-sided figure in which all the angles are right angles and all the sides have the same length but is not a square. And you guys struggled with that one until finally someone said, it's impossible. And the reason why it's impossible is if you have four right angles and the sides are the same length, that is a square. It must be a square. So there's nothing else you can draw that matches those without it being a square. All right, this whole unit, we started off with the mystery of the pocketed protractor. If you were absent, you can read it. It's on page 202. And you see that we solve the mystery by using what's called a Venn diagram. So Venn diagrams is one tool of logic, and you're going to use other tools of logic that are really important to the understanding of mathematics. So we're going to apply these logic tools to really advance your understanding of sets of numbers and shapes and sets of shapes. These are three very important words for logical thinking. The title of Chapter 4 is Representing Sets of Numbers and Shapes, and this first lesson is about these three important words. So we can say a generalization is either always true, sometimes but not always true, or never true. So in your groups you brainstormed some generalizations, and you guys came up with things like once you're born and you're growing, as you grow, you always put on more weight and more mass. And that seems like it's always true. And you said things like people who are really tall usually have big feet, and that's sometimes but not always true. You could have a tall person who doesn't have big feet. So we'd brainstorm lots of those in class. In our quad squad activity, we discussed the generalizations that we'd made about parallelograms. So the opposite sides are parallel and congruent. These are all quadrilateral, so they all have four sides. So if these opposite sides are parallel and congruent, we have a parallelogram. And rectangles. Rectangles are parallelograms, but they must have 90-degree angles. So these must be right angles. And trapezoids may only have one pair of parallel sides. The other two cannot be parallel. And generalizations about rhombi, which is plural of rhombus. This is a parallelogram with four equal sides. And a square. Well, a square has four equal sides, and it has four 90-degree angles, and it's a parallelogram. So a square is a rhombus also. It's a rectangle. It's a parallelogram, but it's not a trapezoid. And so we discussed this idea of a counterexample. If I'm trying to prove something in math and somebody can find one example that goes against what I'm saying, then what I just was saying is always true has been disproven. And it might be something that's sometimes true. So we used our same shapes to talk about this. I said, are all rectangles parallelograms? And you guys drew some rectangles, and you saw, do they meet the features of parallelograms? In other words, in rectangles, do they always have opposite sides parallel and congruent? And they do. So rectangles are always parallelograms. Then we turned it around. Are all parallelograms rectangles? Well, we can draw a parallelogram that is a rectangle, and we can draw a parallelogram that's not a rectangle, and that's why it's sometimes. Are all squares rhombi? Well, if I draw a square, does it meet the categories and the aspects of a rhombus? Well, all squares have four equal sides, and all squares are parallelograms, so squares are always rhombi. Are all rhombi squares? So we turn it around. Well, this is a rhombus that is a square, and this is a rhombus that is not a square. So it is sometimes true. Okay, then we use these same ideas, only we looked at numbers. Are these statements sometimes but not always true? Always true or never true? So you discussed it with your partner. Multiples of 5 end in 0. So somebody said, well, 20 is a multiple of 5 and it ends in a 0. 25 is also a multiple of 5 and it does not end in 0. So it's sometimes true. Multiples of 4 can end in an odd digit. Well, the multiples of 4 are 4, 8, 12, 16, and notice that they are also the multiples of 2, but they're every other one. So every multiple of 4 is in the multiple of 2 list, and those are all even numbers, so it's never true. Multiples of 6 are also multiples of 3. So these are the multiples of 6 in green, 6, 12, 18, 24, 30, 36. And these are the multiples of 3. So what this statement says is that all of the green numbers are in the blue list, the multiples of 3. Well, 3 and 3 is 6. So every other number is not one of the 6 multiples, but every other number, starting with the 6's, these are all multiples of 6 and 3. So this is always true. And then we talked about sets and set notation. So to think about these ideas more clearly, we often group them into sets. And a set is just a collection of objects called elements or members. No different than if you had a set of shells, seashells. It's just a collection of seashells. So, but we do use special notation to show a set, so we use these brackets. And I asked you to look at this set of even numbers from 2 to 16, and what can you generalize about the ones digit of even numbers? And you guys came up with it. If it's an even number, the ones digit is always either a 0, 2, 4, 6, or 8. And that generalization is true for all situations. So there's a special mathematical word that we use when something is true for all situations in mathematics, and it's property. So if you want to identify a property of the set of squares, let's say, here's how. Step 1, draw some squares. And make sure when you're drawing them, you recall what you already know about squares. You know they have equal sides, and you know that the angles are 90 degrees. And then I had each of you write down one fact that's true of every square. And you came up with all sorts of facts. You came up with that they have 4 equal sides, they have 4 right angles, that every square is a rhombus, that every square is a rectangle, that every square is a parallelogram. And that was excellent. And then another set of items, only this time it's a set of odd integers. And I said, find a property of the set of odd integers. Step 1, write out some odd numbers. So you wrote out 10 to 15 odd numbers. Look for some patterns in them. And I said, write a fact that's true for every odd number. So some of you said they always end in 1, 3, 5, 7, or 9, which is true. Somebody else said that every 6th number, the digits are going to repeat in the ones place. So for example, this is the first number and this is the 6th number, and we get another 1, and the next number is 13, and 3 jumps after 3 is 13, or 6 jumps after 3 is 13, so that was true. Somebody else said you cannot divide odd numbers by 2 and get an integer. Excellent. You're always going to get half of something. Okay, then we got up and danced around, and I had you work with a partner to try to think about whether each equation was always, sometimes, or never true. So you danced about, and when the music turned off, you joined up with a partner and shared your thoughts about this. And some of you gave examples. You said, oh, well, if m is 1, 1 and 5 is 6, and 5 and 1 is 6, so that's true. But to prove that it's always true, you have to have a better reason than just one example. And the commutative property is a property that proves that this is always true. And it just says when you add, the order in which you add does not change the answer. So m plus 5 is the same as 5 plus m. And then you looked at this one, n plus 3 is 5, and you came up with that is sometimes true. It's true if n is 2, because 2 plus 3 is 5, but it's not true if n is 10. 10 plus 3 is not equal to 5. And then you looked at this one with your partner, and you gave it some thought. And some of you thought it might sometimes be true because you thought q could be 2 different numbers. But whatever q is in the left side of the equation, because I use the same variable, q is the same thing on the right side of the equation. So somebody said, well, what if q is 1? 1 and 5 is 6, and 1 and 13 is 14, so it's not true. But to prove that it's never true, You have to think of a bigger reason. And finally somebody got it. They said this side of the equation is always going to be 8 bigger than this side because 5 and 8 is 13. So if Q is the same, 13 is always going to be bigger than 5. And so this sum, whatever Q is, when we add it to 13, is always going to be 8 bigger than the sum of Q and 5, which is true. All right, then we looked at different Venn diagrams because we want to find a way to solve logic problems. That's the whole purpose of a Venn diagram, because it shows the relationships between two sets. So there are 3 different ways it can show them. If set A and set B have completely different elements, we say they are disjoint and the circles are separate. If A is a subset of B, in other words, every element of A is also an element of B, then we say set A is a subset of B. And if A and B overlap, that means in this shared region here, that these items here belong in circle A, and these items here also are in circle B. So the overlapping elements would be the elements that belong to both sets. So I showed you some examples to make them real. So if A and B are disjoint, and A is a set of even numbers, and B is a set of odd numbers, well, if you're an integer, you're either odd or even. You can't be both, so that's why they're in 2 separate circles. So those sets are disjoint. Every dog is a mammal. All dogs are mammals. So the set of dogs is a subset of the set of mammals. So D is a subset of M. And the third one with overlapping, so set A is the multiples of 3. Here's set A, 3, 6, 9, 12, 15. And set B in this circle is are the multiples of 2. 2, 4, 6, 8, 10, 12, 14. And I had to put the 6 and the 12 in the middle because notice that when I list the multiples, 6 is both a multiple of 3 and 2. 12 is both a multiple of 3 and 2. So they have to go in the middle because they overlap. And then we did some problem solving. So we're going to use the Venn diagram to solve a problem. So the marching band in a school had 30 members. The school choir has 25. 8 students are in both the band and the choir. And my question is, how many students are in band or choir? How many total students is that? So first of all, in problem solving, step 1 is to understand the problem. So I had you write down the key facts. The band has 30 elements. The choir has 25. 8 are in both, and the question is how many students are in band or choir. So you talked about which kind of diagram is needed, and you guys decided a Venn diagram that's overlapping makes the most sense. So let me just erase this and go over how we went over in class. So we knew that 8 students go in the overlapping region because it says 8 students are in both. And we know that this circle, B, has to have 30 in it. Well, we already have 8 in it, so 30 minus 8 gives us 22 that are outside the overlap part. And with the choir, we have a total in the choir circle of 25. And right now I have 8 in the choir circle. And 25 minus 8 is 17. So that's what you do to find out. That's what you get. And now if I want to know how many students are in band or choir, I add 22 and 8 and 17, and I get 47 students. And then the last step, remember, is always checking your work. So I check the red circle, 22 and 8 is 30, that checks. I check the green circle, 8 and 17 is 25, that checks. I check my overlapping region, I have 8 in both, and that checks, and I know my answer makes sense. And then we did one last one with you with your partner. This is the 6th grade class at the American School of London. 45 students will celebrate their next birthday on a Tuesday. 25 students will celebrate their next birthday in March. And 10 students will celebrate their birthday on a Tuesday in March. And my question is, how many students will have a birthday in March or a birthday on Tuesday? So first of all, you had to decide what kind of a Venn diagram will work for this. And you decided an overlapping Venn diagram. So we put 10 inside of our overlap. And then remember, in the Tuesday circle, we know that there are 45 altogether, because it says so right here. And we already have 10 here. So 45 minus 10 is 35 outside the overlap. And 25 students have their birthday in March. So in this circle, we have to have a total of 25. We already have 10. 25 minus the 10 means that we need 15 outside the overlap. And now we add 35 and 10 and 15 is 60. And if we look back to check it, again, we add 35 and 10. There's our 45. 10 and 15, there's our 25. And we have 10 in the middle. So we absolutely know we're right. Okay, you have some homework practice to do. I had 4 people after school today, Friday, so Monday's the last time to do that retake. If your project is late, get it into me. I'm grading them this weekend. I'll see how many I get through, but you'll be staying on a Monday study hall if you don't get it finished. All right, that's it. Have a great weekend.